Hello? Hello. Okay, we're ready to get going. We are starting with our, what week is it now? Week 7. Week 7 Senior Experience Talks, and Carmen is going to start us out for the week. She is going to be introduced by Graham Sathema.
Hello, everybody. I am very happy to introduce Carmen Magestro, who comes to Lawrence from Cudahy, Wisconsin, near Milwaukee, for those of you unfamiliar. Let's see, Carmen is a double degree student in flute performance and chemistry and biochemistry. Okay, so that's actually, double degree, double major, doing it all. And Carmen joined my group right after our COVID summer. So she was able to spend one summer working with us here in the lab, mask-free. It was a real, we all needed that really bad that year. So I think we all were happy to be there. And has done a lot of really good work advancing one of the luminescent radicals in our group that she's going to tell you about today. So after this, Carmen is headed to grad school at the University of Notre Dame. I got that right? Okay. And yeah, we're looking forward to seeing what happens after that. So with that, Carmen, take it away.
Cool. Oh God, that is louder than I thought. Okay.
Try now.
Hello, hello, hello. Oh, that sounds a little better. Cool, great, cool, sweet. Thank you for the introduction, Graham. And thank you everybody for coming here in person and on the Zoom. I'm really appreciative of everybody joining me today. So today my presentation is going to be on the incorporation of the chromophore pyrene into the stable radical BDPA. So I'm sure screens are a really big part of your everyday lives. You probably look at a screen every single day, especially if you have a cell phone or a laptop. Screens are important for everyday communication, entertainment, and also virtual learning, as we've seen in the past 2 years. And technology is being improved every day, and a way that these screens are being improved is by the incorporation of OLEDs. So I'm sure you've heard of OLEDs before, but what actually are they? OLEDs stand for organic light emitting diodes, where the pixels are self-emitters of light. And you can compare that to LCD screens that are liquid crystal display screens. And this is where there's actually an extra backlight because the pixels do not self-emit light. And as we can see from the photo, that these OLED screens are a lot brighter and sharper in its image. And that's a big reason why they're being incorporated into a lot of new technology, especially like the famous Nintendo Switch. So this is a really big pro of the OLED screens, along with they're actually thinner than LCD screens, so it requires less material to operate these screens. But with all pros, there also comes some cons. OLEDs are not super efficient. So red and green diodes have about 20% efficiency, while blue diodes are even less at about 4 to 6% efficient. So what could we possibly do to increase this efficiency? And to increase the efficiency so that we can have optimal performance of these screens and possibly have a longer lifespan? Well, it's all connected to what make these diodes self-emitters. So my project with Graham's research deals with finding molecules that have more efficient luminescence. And a way that we can make that happen is by thinking about what is happening within the molecule that allows for luminescence and how can we increase that efficiency. So we can visualize luminescence through these graphs that kind of show the visual pathway of what the electron is going through to create either fluorescence or phosphorescence. But this graph is really complicated. You don't have to worry about this just because I wanted to show you how complicated it can get, and this can result in this decreased efficiency in some molecules that luminesce. So this research proposes that if the pathway of the electron is a lot simpler, it's going to make the luminescence more efficient. And basically, this can be done with molecules that have these doublet states. So that's what the D denotes on this graph. So D0 denotes the ground state, and then any states above them is D1, D2, going all the way up, and those are the excited states that the electrons can be in. So if we break down this graph a little more, we see that the blue arrow deals with the absorption of some kind of source, and then we're just going to worry about the green arrow that deals with the emission of light in response to that absorption of some light source. So a molecule that has doublet states means that it only has one unpaired electron, and this unpaired electron will be responsible for the luminescence. And luminescence is produced ultimately by a UV source being shined on the compound. The electron gets excited to the top state, and then once it relaxes back down to the ground state is when we see visible light. But if you shine a UV light on every single compound in the world, they're not all going to luminesce, because we need to have something called a fluorophore to allow for luminescence in a molecule. So with our research, we first are looking at how can we pick a good fluorophore for ultimately this luminescent radical. So there are many different kinds of fluorophores. I only picked out a few for some examples. Some of you may know some of these. There's rhodamine red, fluorescein that I know is used in a lot of bioimaging, and but these two are fairly expensive. And then we have something like anthracene or pyrene that is less expensive and more abundant. And then I just put bodipity in because I thought it was a cool name. But bodipity is pretty expensive too. So we decided to go with pyrene because it's abundant and it's pretty inexpensive, which is good for our research. So to begin with, oh, I'm so sorry. There we go. To begin with, I talked about these molecules that have doublet states. For a molecule to have a doublet state, it needs to have an unpaired electron. So molecules that have unpaired electrons are called radicals. And if you don't know what a radical is, I'm just going to go through it really basically so that we're all on the same page. If we have a molecule like methane, CH4, carbon has 4 electrons. That's going to want to have, that means the carbon is going to want to have 4 bonds. But once we take away one of those bonds and leave that one electron on there, that electron is no longer paired. And electrons really like to be paired. So when they're no longer paired, they become reactive. And that's why when I say radicals, sometimes people think of really reactive species, especially like the superoxide species. But radicals can be stable. So a way in our lab, there are many ways we can make radicals stable, but a way in our lab that we are trying to make the radical stable is by centralizing the unpaired electron onto the center of the molecule. And then you protect it at every single angle. So as an example, this molecule has already been researched by some previous labs. It's called TTM, and it is a luminescent radical. And as we can see here, they have the unpaired electron in the center of the molecule, and it's protected by these phenyl and chlorine groups. So why do we care about stability and luminescence? Well, the goal of this research is to find a stable luminescent radical. And there have been a few that have been researched before. This is the molecule we just saw on the previous slide, TTM, and a lot of research that I was reading in the previous term is if we add different, laser pointer, we add different kind of groups onto the radical, or if we change the structure from within, as we can see here, there's a nitrogen instead of a carbon, we can then get different colors for luminescence, and it also changes the stability of the molecule. So now that we have this background and we see that this research has been done before, what is our stable luminescent organic radical going to look like? Well, like I mentioned before, we picked pyrene as our fluorophore because it's really cheap and it's abundant. And then our radical structure is going to be the famous BDPA. It is a really well-researched radical, and it's very stable, and its all-carbon framework works really well for us to be able to add different pieces onto it. So we are trying to see if we add pyrene on, can we produce a stable luminescent radical? So before we get into the synthesis, we'll just kind of take a quick overview of, we're looking at stability. Does the molecule react with itself, or does it not react with itself or with others around it? Will it luminesce repeatedly? And then is it air and water resistant? And is it luminescent? If there is a UV light on it, will it emit light back? Is it an organic radical, which means is it primarily made up of carbons? And is it a radical? Is there going to be an unpaired electron on this molecule? So for the synthesis overview of the pi BDPA radical, we need to start from somewhere. So these are 2 reagents that we can buy commercially. We start off with 1 bromopyrene and 2 fluorine. And I realized that I should specify that this is fluorine with an ENE and not an INE. If you hear the word fluorine, I'm not talking about the atom, I'm talking about this group right here. And these 2 pieces will ultimately create this 1/2 of the molecule, if we can kind of see that up here, the kind of pyrinyl fluorine piece. And then we need to figure out how to make the other part of the molecule, and then ultimately we can make the molecule and then the radical. So I'm going to start off with this part, the pyrinyl fluorine, because this took the majority of the summer because it was a little tough to get through. But we got through it. So with this molecule, we need to figure out how to make a carbon-carbon bond, as we can see here. And a way we can do that is through cross-coupling reactions. So I'm going to go through a general mechanism of what a cross-coupling reaction is, and then we'll get into more specifics about what we were trying for our research. So the cross-coupling reaction starts with some kind of palladium catalyst. The first step is called oxidative addition because we have, as we can see up here, our group of interest. This is the part of the molecule that we care about. And currently it's attached onto some kind of halide. And this halide is a good leaving group, and that's the reason why it's attached onto the group of interest. And these 2 groups get added on to the palladium catalyst. And then in the next step, we have transmediation, where we see our other R group of interest. And currently in this step, it is bonded to some metal, and then the metal will exchange with the halide so that we get both of our R groups of interest onto the palladium catalyst. And then the last step is reductive elimination, where the palladium catalyst gets reduced, and these 2 R groups will form a bond between each other, and then our catalyst regenerates itself. So the initial plan was to use the Stille cross-coupling reaction to make our pyrinyl fluorine. So now I'll go through the cycle again, but with a little more specifics. We have some kind of palladium catalyst, and this is where we add in that 2-bromofluorine, as we see here. We have the oxidative addition, where both of these, the bromine and then the fluorine, gets added onto the palladium catalyst. And then we have the transmedylation step. And we see here that what makes the Stille cross-coupling unique is that it uses an organotin coupling partner. And then we have our 2 R groups of interest being bonded onto the palladium catalyst. And then we have reductive elimination, where the palladium catalyst becomes reduced, it regenerates itself, and then we have our end product of interest. But before we can even start the cycle, we need to figure out how to make the transmedylation partner. So we can do this by having that 1-bromopyrene that we bought, introducing it to some tributyltin chloride, and through a pretty standard Grignard reaction, we should have made this product, but spoiler alert, it was unsuccessful, and I'll show you why we think that is unsuccessful. So for this, I'll be showing you some Gcms scans of my sample. So Gcms is a really neat instrument because after my compounds mixed in the reaction overnight, I could take a crude sample into the instrument, and the instrument will be able to separate the compounds in the sample. That's the GC part, gas chromatography. It will separate out the molecules in the sample. And then the MS stands for mass spectroscopy, where it will be able to detect the mass to charge ratio and then ultimately the molecular weight of the molecule so that we can kind of detect what is in the sample that I just put into the instrument. So the top here, I have my experimental data. And what's really neat about our instrument is that it has a library database that it's connected to that it can compare my scans with. And as we can see here from the library database, it picked up 1-bromopyrene. And if we remember what 1-bromopyrene is, it is the starting reagent of my synthesis. And what's really neat with the separation part is that it separated this from this molecule, which is the other starting reagent of the synthesis. So if we had the starting reagents that didn't react with anything, that means we did not form this compound at all. And that was kind of sad because it took quite a bit. I tried many different reactions and tweaking the reactions, and I still couldn't get this to work. So we just moved on. And instead of a Stille cross-coupling reaction, we moved on to a Suzuki cross-coupling reaction, which if you took organic chemistry, you definitely know about. So we have the catalytic cycle again, and as we can see, we have some palladium catalyst, and the first step looks exactly the same, where we had the oxidative addition. Then the transmediation step is where it's different, where instead of a tin, we have a boron here. And then same process again, where we have the two are groups of interest being attached onto the palladium catalyst. The catalyst gets reduced, and we have our compound of interest. And again, before we can even start this catalytic cycle, we need to make the transmedation partner. So to make this piece, we have the 1-bromopyrene, and we introduce it to bis pina colada diboron, which is like the coolest name ever. And then we have some base, some catalyst, and I put a picture of the catalyst because I think it's really cool because I made this in inorganic chemistry class, so it's really nice to be able to make this again in the research. And then we get our transmetallation partner. And what's actually pretty neat is that this is also a Suzuki coupling reaction to ultimately get to the molecule we need to make a different Suzuki coupling reaction. So from here, this is just to show you that after my reaction had stirred, is a really dark black, which is the palladium black. And after a lot of filtering it and purifying it, I was able to get a transparent yellowy liquid color, and it luminesced blue upon UV rays, which I thought was really neat. That's like my favorite photo ever. Shout out to M for taking it. So this reaction was successful, and a way that we can see this is through the Proton Nmr. So the Proton Nmr, if you're not familiar with it, it will basically tell us how many protons are on this compound and about where in the molecule are these protons. So I have zoomed in on the upper region of this graph so that we are only looking at these protons, at these hydrogens here. And we have, this part was fairly easy because it's in the literature already. So I was able to take the literature's data and be able to compare it to my own graph here. So we do see that triplet at about 8 ppm, and we do see that multiplet that follows it, and the two doublets a little more upfield. So because it's already made in the literature, it's pretty easy for us to say, yes, we made this molecule. So up next is we can actually do the Suzuki cross-coupling reaction to make that pyrinyl fluorine, where we have this piece that we just saw on the previous slide, and we can now add the 2-bromofluorine. And through some base and palladium catalyst, we get our pyrinyl fluorine, which after purification, I got a solid that luminesced blue. So here, the Proton Nmr, I took another Proton Nmr of this, and for this one, this is not in the literature anymore. So we kind of had to inspect it ourselves to be able to see if we think we made what we think we made. So this molecule has 18 hydrogens. And as you can see here, I highlighted some hydrogens red, and then we see two that are a little different that are not highlighted. So I have zoomed in on this Proton Nmr spectrum to only show the highlighted hydrogens here. And these are about 16 hydrogens, which we do see up here. And the reason why they're different is because if we can see, these hydrogens are bonded to double bonded carbons, while these are not bonded to a double carbon bond. It's only bonded to a singly bonded carbon. So for those who took organic, that's the difference between the sp2 hybridization versus the sp3. But if you don't know what that means, don't worry. It's basically that they're going to show up differently on the Proton Nmrs. So because we know these two are different, we know they're going to show up differently on our graph. So now if we zoom out of our graph, we see that these two protons show up here around 4 ppm. So they're shifted a little further down on the graph. And that's when we were able to say we think we made this molecule, and we're going to move on with the synthesis. So back to the synthesis overview. We have made this part of the molecule, and the next step is to make this other part of the molecule, which is our substituted alkene. And a pretty well-established reaction that we can use to do this is called the Horner-Wadsworth-Emmons reaction, where we have this big molecule that's very expensive, added in with some fluorinone, which is not expensive. And just to point out, this is a fluorine piece, but it's fluorinone because we have now a new carbon-oxygen double bond, so that makes the naming a little different. But this reaction will then yield the substituted alkene, which is the left part of our molecule. And back to using GCMS again, I was able to put in a sample into the instrument where the instrument was able to say, yes, we found what you made. So this is when we were able to say that the synthesis was successfully created, or the synthesis was successful, and after purification, I got these yellow solids. So now going back to our overview, we have made our two kind of intermediate pieces. We can now move on to make the molecule and then thus the radical. So for the formation of the molecule itself, we have the two pieces that we have made. And after the addition of some base and then some HCl, we get the molecule. And I did this on the benchtop, and it seemed pretty robust because we actually ran out of nitrogen, and it was late one night, and nobody could fill up the nitrogen. So Graham was like, go for it, and we'll see. So I did, and it turned out fairly well, or so we hope. So then I moved on to make the radical from this molecule that I made. And because we're making the radical now, we wanted to be a little more careful because we don't know 100% if the radical is going to be stable right away. So I did this in the glove box, and the glove box is basically an enclosed box that has no air, no water, it's only inert gas. So after that, or after doing it in the glove box, it didn't take too long. It really only stirred for a little more than an hour. I put some crude sample into an EPR tube just to see at first if it would luminesce under UV light, and it did luminesce, as we can see here, and it's about a yellowy color. And then I took an EPR scan of this. So EPR stands for electron paramagnetic resonance, and it will be able to detect unpaired electrons in my sample. And what I was trying to use it for was ultimately just to see if I had made a radical. So if we see some signal, I made a radical. If I don't see anything, there's no radical present. And as we can see here, there is definitely a radical present, which is really neat. And then we have, this is more of newer data. I'm still trying to understand it a little bit more, but I wanted to show you a little bit of this. So what you're looking at is an absorption line and then an emission line. And we have this peak here, which is about like 538 nanometers, which corresponds to about a yellowish color, which is what we see in my luminescence. So that's really promising. And then in summary, just to wrap everything up, we are interested in making self-emitting molecules more efficient, and we can do this by looking at what is causing this luminescence. And we can ultimately use a radical that has doublet states to make more efficient luminescence, and we're doing this by creating pi BDPA. And we think we've gotten to the end of the radical, although we still need more analysis and purification. But as of now, kind of looking at our small little checklist, we would say it is stable enough. I made this radical back in February, and I think the last time I took scans was about 2 weeks ago, and they're still radical, which is really neat. Luminescence, we say maybe, because there is a small chance that that yellow luminescence is actually from an impurity. I did do a purification step, and on TLC, it showed 5 products in the sample, and then it went down to 3 products. So I did eliminate 2 impurities in the sample, but there is still 3 kind of products in my sample. So that means it's not quite pure yet. It is organic. It's all made up of carbons, yes. And then it is a radical, as we've seen on the Epr spectrum. So moving forward, we need to further purify BDPA. And then from here, we'll be able to further study the luminescence. So we can really see if this yellow luminescence is from the radical or if it's from some impurity. After that, we can take some more Epr spectrums and look at where is this unpaired electron on the molecule in relation to all the hydrogens on the molecule. So where is this unpaired electron basically placed? And then we can use computational chemistry calculations to kind of look at the optimal geometry structure of our molecule. And then we'll be able to create other derivatives, hopefully, using pyrene and BDPA. So can we put pyrene on maybe one side of the molecule here, as we can see? Or can we kind of make it look a little mirrored where we put pyrene on both sides of the molecule? And then from here, we can look at how does the luminescence change, if it does, and then also how does the stability change by this additional pyrene onto the molecule. Thank you for coming to my talk. I'll take questions now.
Excellent. Does anybody in the in-person audience like to ask a question? Carmen, call it as you see it.
Allison.
So you said that you're pretty confident that it's stable. So what's the normal lifespan of these things? So like if best one you can go and buy off the shelf, what does stability look like for that? Or just an average one?
That's a good question. I'm actually not super sure. I know the TTM radical, that first one I showed that another research group looked at, that one has been pretty stable, like more than the one I made, but I actually am not super sure what the average
Yours
is.
is stable for months, at least you have some sort
Yes.
of measurement.
Yeah.
Is there a way to do a percent loss of that? Like an intensity question?
I think so. We could. What I am thinking is maybe we could take the Epr spectrum or spectra and look at the intensity and maybe see how that intensity decreases after so much time outside of the glove box. I have not done that yet, but that would be important to do. Yeah.
Just curious.
Yeah. Thanks.
Other questions?
Ezra.
Yeah, the first reaction that you showed us, I forgot what it was called, the cross-coupling one.
Sure.
And we were like, oh, this didn't work. Do you know why it didn't work or what went wrong? And do you have any idea what you could do or what someone could do in the future to try to run it to make it successful?
Yes. That is something I forgot to mention. Let's see. Yes. So we kind of hypothesized that this didn't work because, as we can see here, pyrene is pretty big, and so is this tributyl tin piece. And we're thinking that steric hindrance was playing some effect, and it just wasn't in our odds for these two to interact with each other, just because they are fairly bulky pieces. And what I had done, I changed different aspects of the Grignard reaction, and then I used N-butyl lithium as a strong base to see if that would work. And I did that like in the cold bath, and then I used the cold finger, which is really cool. I got a cold bath down to negative 96, I think, Celsius. And then it still didn't work. I actually think that may have produced even more products. So as of now, I'm not entirely sure what else we could do to make this work. I'm assuming we would maybe have to get away from the Grignard reaction and then using N-butyl lithium and try something completely else. Yeah, that's just what I'm thinking.
We have a question from someone on Zoom, Mike Foley. I believe you know who that is. Do you have an estimate on the efficiency of your synthetic reactions? I'm not sure if that's possible to estimate or not.
Yes. Would that be like yield? Is that what you're asking? Okay, yes. So the yields reported, I didn't have them on here just because I ran these reactions a few times, and typically the yields I've gotten as low as, well, very low, but for a good reaction was about 20% as a yield, and then I don't think I added it on here, but one of my reactions was at about 20% for the yield, which is pretty good, I would say. Yeah, and that might be related to me learning how to do these reactions for the first time, and also the starting material. We didn't really check. We just kind of trusted the purity of the starting material that we had bought. So if I am doing these syntheses well enough, maybe the next step would be to check these starting reagents to increase the yield. Yes, yeah.
All right, I have a question too about your moving forward slide, your future goals. You had the pictures of the other possible derivatives you might make. One of them looked like it was more symmetrical. Do you think that one would be more difficult to make because of the steric hindrance around the center?
So this one, trying to see, I could see it maybe playing into it, because I'm thinking if we made this part already, we would make this kind of like substituted alkene, and before we attach it onto this part, we would attach this pyrene on first, which would require some kind of like another like 2-bromofluorine piece here. So I guess my answer is I'm not super sure. Nothing sticks out to me right away that says that may be a really big issue. I could see a maybe, but yes.
I'll take that. Any other questions from our in-person people or our Zoom people?
Professor Stoneking.
Yeah, got a physics question, I guess. Chemistry question. You said pyrene is a fluorophore, so what in general is a fluorophore?
Yeah, that's a good question. So if we think about, sometimes the confusion comes from like chromophore and fluorophore. So if we think about chromophore is the part of the molecule that's responsible for the color, and then fluorophore is part of the molecule that's responsible for the luminescence. Because if we're looking at different items right now, everything has some kind of chromophore that's giving it its color. But if I put a UV light on the table, it's not necessarily gonna luminesce. And that's because maybe the table doesn't have a fluorophore that gives it its ability to absorb light at one wavelength and then emit it at a higher wavelength, which would be the luminescence, if that makes sense.
And then to make it, by making it a radical, you want to make it more efficient luminescence.
Yes, yeah, because the radical will only have that one electron that will just like go up when it's excited and then relax back down, and we don't have to worry about like it crossing over to other states.
All right, we'll call it there. Let's thank our speaker again. Excellent, loved it. Please join us on Wednesday and Friday at the same time for even more of the same good stuff. We'll see you then.